Hello, good evening to everybody. So as you hear, today we have an English talk and I'm very happy to have good evening to everybody. So as you hear, today we have an English talk. See, I told them that it will happen and now it happened to me. Great. Even after 2 years, still happening. So yeah, we're still researchers and not YouTube streaming pros. So yeah, I'm happy to be here today. My name is Corinna Peter. I work at the Alfred Wegener Institute, the AVI, and my research focus is on the restoration of native oyster reefs, but also a little bit on blue carbon in the German northern Baltic Sea. So I'm very interested about the topic today. Yeah, I'm happy that you joined. If you have any questions during the talk, please always feel free to write the question in the chat and we will have a look on it. And then we will forward the question to Santi and Narissa after the talk. So yeah, keep us posted with your questions. And I have a colleague of mine with me and yeah, she's up next.
Yeah, good evening. I am Rebecca and I'm also a researcher like Corinna at the Alfred Wegener Institute. But I'm a physical oceanographer, and so I look at the warm water that is on the northeast Greenland shelf and which melts the glaciers up there. So a little bit further away from the blue carbon, but you know the ocean is all connected, and so I'm really looking forward to hearing what Narissa and Santi will talk about this evening. And so it is now up to them to educate us all in their exciting and cutting edge research.
I will start on to the presentation evening. I'm Santi for short, also from the AVI. I used to be working on the Southern Ocean, which is part of what you're going to see soon, but now I'm in the North Sea, also working with the oysters and the restoration of them with Corinna. Now let's go for the presentation. There we go. Evening, everyone. Once again, thanks for the presentation. And today, Narissa and myself are going to tell you a short story on blue carbon research with a focus on the Southern Ocean and the subantarctic side in Patagonia. With that, I leave you with Narissa.
Thanks, Santi. So blue carbon in the broadest sense is the capture of CO2 into the tissues of plants and subsequent storage in animals. Tropical mangroves, seagrasses, salt marshes are the most commonly recognized important blue carbon habitats, and they store carbon like trees and are a source of carbon emissions if degraded or destroyed. So this is an easy analogy that is relatable to terrestrial deforestation, for example. Unfortunately, these mostly tropical habitats are very small in area and are in decline. Our research is trying to understand blue carbon in more polar environments and is particularly focused on the seafloor, the site of sequestration. Next slide. So this graphic visualizes carbon capture, storage, immobilization, and sequestration across time. When marine animals die, some of the carbon is stored in their bodies and their skeletons can be buried in the seabed sediments. This removes the carbon from the carbon cycle, and this long-term removal is genuine sequestration below the anoxic sediments on the seafloor. Thank you. On the seafloor, our research focuses largely on what are known as vulnerable marine ecosystem indicator taxa, which occur across locations such as corals, sponges, bryozoans, and brittle stars, which have a calcium carbonate skeleton. Making them important is what is known as ecosystem engineers, providing the structure of the seafloor communities. But due to their life history characteristics, which are often slow-growing, long-lived, late to reproduce, and they're fragile, they're also considered at risk from direct threats such as fishing and comorbid impacts such as ocean acidification and warming, with various capacities for biological responses to change. There is this sort of pervasive idea that because Antarctica is isolated, that it is pristine. especially somewhere so out of sight and out of mind like the seafloor, that everything is fine, that there's no threats. But sadly, this is not necessarily the case, given the typically slow growth rates, low annual productivity, and economic interests in Antarctica. So as this image in Brazier et al. 2021 illustrates, we will see changes in seafloor assemblages from the undisturbed state in the centre, with different responses to warming, fishing pressures, ocean acidification, and in relation to changes in sea ice and scouring on the seafloor as well. An emerging part of this conversation for fisheries management focuses on how much carbon is taken out of the ecosystem in terms of the fish species themselves, but also the other animals that may be removed as bycatch and as a consequence not sequestered on the seafloor. Next slide, please, Santi. So this is from our publication in 2020, where we created a graphic which tries to illustrate the natural carbon sequestration of the Antarctic continental shelf and how this capacity is increasing with warming and across a vast area. So this exacerbation of blue carbon storage at the poles is what Dave Barnes terms the bluing of the poles. And this is a shift from white to blue, attributed to a negative feedback loop linked to Earth's albedo effect. So ice has an especially high albedo. As ice decreases, the albedo effect is reduced, and there is subsequently an increase in the heat absorption of the ocean. Although it may appear low in terms of carbon storage per unit area or volume over time, the sheer magnitude of the area available in the Antarctic continental shelf multiplies up a small value to a considerable one, and this represents the world's largest increasing natural form of carbon storage with high sequestration potential. These high latitude blue carbon gains are now 3 of the 4 biggest natural feedbacks on climate change. A feedback acts antagonistically. None of these feedbacks are strong enough, at least at the moment, to actually reduce physical change. They merely decrease the rate of increase, i.e. they reduce the potential for greater increase in the face of climate change. Of the known negative feedbacks, all of them are polar, and 3 of the 4 are blue, so they're marine, blue carbon. They include, firstly, the broadening of existing sinks with sea ice losses over polar continental shelves. Because phytoplankton gains in time and space, this is the focus of our work, and the most important sink by far, just because the area is so large. Secondly, the formation of new sinks where ice shelves collapse. And thirdly, new sinks from glacier retreats opening up in fjords. To illustrate this, Santiago is going to talk about our understanding of bluing and whitening through the lens of 2 case studies, firstly the northeastern Weddell Sea, and secondly on the West Antarctic Peninsula. And I'm going to briefly introduce some work in the subantarctic to extrapolate the idea in locations like the Falklands, for example, where I'm based, where this work is also important for a biodiversity conservation standpoint, which also translates to a nature-based solution to climate change.
Now I'm back, building up on this bluing and whitening. I prepared this little graph where we have Antarctica as a whole, and we have these patches of blue and gray, where gray is the areas where we won ice along the years, in this case in between the late 80s and last year during summer. Here summer is the important part because it's where most of the production is made when the sea ice retreats. And then the blue ones, the bluing, so areas where we've lost the sea ice. This is in the temporal scale. It's also important to know that ice plays a role in the space also. And this is an example of what it looks like in average during summer. And here, the white parts are where you have the most ice, is where it's fully covered with ice, and the moment it gets bluer, so the amount of ice decreases. For Avi and colleagues from the British Antarctic Survey, the main study region has been within this red box, which is on one side the Weddell Sea, and on the other side the Antarctic Peninsula. If we zoom in within the box, here you find, for example, Neumeier, the German Antarctic base, and again this concept of you have a lot of ice, especially in the middle of the Weddell Sea, and then it decreases towards the north and east, and the peninsula with almost no ice during summer. If you were to take a picture to see how it would look like in terms of carbon, blue carbon in terms of animals, you will see that for the really white area, it looks really barren, almost no animals at all. Whereas the moment it starts getting bluer, you start finding these sponges, which are the typical bioengineers that you have there, and where you have the most biodiversity and the most blue carbon storage. What we've done, and I come back now to the whitening, and the bluing. We have that for the Weddell Sea, a good part looks grayish, so we've gained ice in the last years. And what I focused during my time as a polar research was what happened in between the period from the late 80s until 2014, because that's the latest period from where we have the data. And being part of AVI, our main research area has been the small circle here, which is 2 bays, Cap Norvig and Austassen. They appear small in the map. They are around 9,000 square kilometers, which is something like 20 times Berlin or Puerto Rico in area. So it looks really small in the map, but it's actually not that small. As I said, we've done this thing for some year at the Institute, and here what the graphs show, it's what happened in terms of changes in the sea ice and changes in the benthic blue carbon from the mid-80s until the mid-2010s, so until 2014. And on the red, we see that the first part, the first 10 years, 20 years until the 2000s, we had really low sea ice cover, and it increased during the year. And contrastingly, we've lost the stored blue carbon we had there, with a loss of around 2/3 of what we used to have by around the 1980s, 88, 89. Again, using pictures to give an example, we have at the beginnings or in the mid-80s, we had a lot of sponges there. We had a lot of biodiversity, a good amount of blue carbon stored, and due to the increase of sea ice, it looks now a bit more like this, with more dead animals there. So maybe a bit sequestered carbon still there, but not that many stored. What does this mean? What's the bigger picture here? If we take into account other whitening shells, so we have the Weddell Sea, the Ross Sea, and somewhere here in East Antarctica also, what happened there? According to what we estimated, we've lost in this 26-year period around 18.5 tons of carbon. Put it in another way, it's the unit of measure you usually use is the carbon equivalents, which were 69.3 megatons of it, or what 50 million cars produce in 1 year in terms of carbon, which if you put it in an economic way, it's 4.5 billion euros to today's cost of a ton of carbon. And put in really plain and simple and nice ways, it's what the top 5 leagues in the UEFA spent in 2020 to buy football players. To give an idea. It's not all bad. There is a good side to it, and with colleagues of ours from the British Antarctic Survey, Dave Barnes, so he also had some data from the Amundsen Sea, Bellinghausen in the peninsula, also sub-Antarctic islands like the South Georgia and South Orkney Islands, and at part in the Weddell Sea. And what he managed to relate is the amount of carbon which is produced by the benthos, of blue carbon, with the amount of days which are free of ice. And the time we start getting more days free of ice, the production of carbon increases. So wherever we have bluening, we're actually gaining blue carbon also. Another nice example of this is in the Larsen area. So here we have the tip of the Antarctic Peninsula. There we used to have 2 ice shelves, Larsen A and Larsen B, which cover the whole blue part here in the graph. Larsen A collapsed around 1995, Larsen B 5 years later, and on one of the Polarsen expeditions in 2007, they managed to get there. They did videos and they revisited some of these transects 4 years later in 2011. The upper picture shows a lot of sea squirts, really low sponges, so the community was building up. And 4 years later, they found that you have more sponges there, and there were 3 times the amount of sponges and 2 times the biomass of sponges, from which we can also infer that the blue carbon stored there, it increased in the same way. That's although that's what happened in between, again, 79 and 2014, where we had this big whitening, especially for the Weddell Sea, and bluing in the peninsula tip. Now, if we were to do something similar, but from 2014 onwards, we saw our colleagues from working on sea ice, they find that it changed completely, and now we have a lot of bluing in the Weddell Sea. And this is what it's good for the blue carbon, because now, since you have more bluing here, based on what I was saying about the amount of ice-free days, you have more ice-free days, you should have more production, then you fixate a lot more carbon in terms of benthic biomass. And this is what we are trying to now figure out on how the animals there then reacted and increased, decreased, stay the same. With that, my part is more or less done, and I leave you with the story of both the McFace and ice and biodiversity.
Thanks, Santi. So this is a graphic from Barnes et al. 2016, made for the work in South Georgia, but it's actually been a really good illustration of biodiversity patterns driven by ice. So as you can see, when the ice is extended during the last glacial maximum, as it recedes, animals are able to come in and colonize. And then when Bodie McBoatface comes along, finds a high accumulation of biodiversity where the glacier ended during the last glacial maximum, and less as you get closer to the ice. And so this has become quite a good illustration that I've been showing people here in the Falkland Islands, for example, because during glaciated times, animals would seek refuge in non-glaciated areas. So the Falkland Islands was non-glaciated during the last glacial maximum. And as a consequence, you have this high accumulation of biodiversity that was potentially, there for a long time, evolving to these conditions. And you also have this unique test case where we can look at blue carbon, but without the influence of ice. So if you go to the next slide, Santi. So subantarctic islands, more broadly, they form this unique geographical, climatological, and also politically diverse region in the Southern Hemisphere. So life on the seafloor illustrates the unique intersection of the evolutionary traits due to their unique positioning at a climate boundary, so between temperate and polar ecosystems, and having experienced large oscillations in terrestrial and marine climates throughout Earth's geological and climate history. Hence, it is a key area for understanding drivers of speciation, biodiversity, and predicting the responses of species assemblages and habitats to future environmental change. They're like biological laboratories for blue carbon research. These islands are also unique in their conservation management needs. So unlike the Antarctic continent, this region does not fall under an Antarctic treaty system and is typically under the jurisdiction of individual countries. As a consequence, science coordination is less well developed and in the region than the Antarctic Treaty Area, for example. In response to this, we created a subantarctic blue carbon and natural archives network last year. So to connect our knowledge on the impact of the paleo and current environments on carbon pathways. This understanding will hopefully inform future conservation and climate change policy by illustrating that idea that past behaviour is key to understanding future responses to change. And the subantarctic encompasses an area across more than 14 million kilometres square. So from the shallows to the terrestrial environments and deep sea. So what our project's hoping to understand and conserves lies on the sea floor, but by combining natural archives with our policy and disciplinary collaborations, what we hope to provide is something broader than that, so a more multi-tier, multi-habitat approach to conservation, for example. And the subantarctic and Antarctica as well. So both of these regions, they're so incredibly unique in this context for their contribution to planetary health, governance systems in which they exist, and the hope that we have if we act now. So especially given marine conservation networks in these locations are like rare case studies in the world where we are protecting in advance of significant visible or perceived direct human impacts, such as a fisheries decline or need for an intervention or an intense coastal development or ecosystem loss, for example. In these locations, there is very little, if any, coastal use and development. So the key consideration is almost solely in relation to climate change. And this is a unique opportunity to preemptively conserve these areas for the future. Next slide. So this is an ongoing collaborative effort to build across countries, and we have collaborators from Peru to Germany and research institutes combining science, governance, law and economics with multiple funders over the years. Many listed on the left are collaborations during my time in the Falkland Islands, so such as the South Atlantic Environmental Research Institute where I work, but I've also listed Coast Carb, who kindly invited me to their General Assembly this year in Punta Arenas in Chile, and the Deep Ocean Stewardship Initiative, who kindly invited me to be part of their Deep Sea Climate Change Working Group delegation at COP27 this year. So this is incredible, but it shows that these ideas are hopefully gaining traction at higher levels of climate policy. And Santiago and I would also, of course, kindly like to thank Corinna, the Alfred Wegener Institute, the Wissenschaft, fürs Wohnzimmer, Science in the Living Room, and Rebecca as well. Lovely to meet you for this wonderful opportunity. And I just wanted to, there's one more slide. Santiago and I wanted to end on this slide because we have a bit of graphics in our presentation, but this one really exemplifies just how beautiful and biodiverse the seafloor is in Antarctica. So I was hoping to end there, and this is actually an image from within the fjords in East Antarctica.
Thank you very much for this great talk and this great image. Yeah, wow, it's very colorful as well. I never imagined it that colorful. Really nice. Thank you very much, Santi, and also Narissa. And I forgot to say before that Narissa is right now sitting close to where she studies, so at the Falkland Islands. So thank you for being here digitally from so far away. Yeah, just a short view into next week's talk. It will be Viktor Smetacek again. So people who watch this channel often know his name and know his talks. So we're very happy that we can have him here once more. And this time he will talk about seasickness, and I guess there will be a bigger picture to it, so it will have some different aspects of research, I guess, but yeah, it's gonna be exciting, and yeah, tune in next week to see how he gets this bigger picture. So it's gonna be exciting. Yeah, but for now we will go back to blue carbon in the Southern Ocean, and we have a question in chat, so I will start asking. So Zebra Twist is asking, how quickly would the biomass decrease again if ice would return to ice-free areas? So whoever feels like answering can do it now.
This is something we calculated also. We related the sea ice increase and decrease to biomass and abundance increases and decreases of blue carbon in this case. And we found that in terms of biomass, they usually react quite fast for what the Southern Ocean is. So within a year or two, you would already see a change, either upwards or downwards, in reaction to an increase or decrease of the sea ice.
All right. Yeah. Thank you very much. And yeah, there is a follow-up question also from Zebra Twist, who's also commenting on this awesome picture. So he or she is asking that it's an amazing biodiversity. At which depth was this picture taken?
Which one
You're
of them?
still muted, Narissa. So,
Sorry, the one in the fjords in East Antarctica.
Yeah.
Yeah, so that's actually taken relatively shallow. It's not by diving, it's with an ROV. And so it would be above the 50-meter mark. And so there is an interesting thing in terms of what we'll find in the shallows and what we've been studying more in deeper areas. I guess my collaborations have been more focused on the continental shelf and offshore, but that is work with the Australian Antarctic Division. And, you know, as you can see from what Santi was talking about as well, it's, you know, the concentration of effort is often on the peninsula, and so there's big gaps in our understanding more broadly. And so East Antarctica is a big gap for Antarctic research, and we're hoping to, would be starting the process of understanding for that area. And it's also interesting in terms of ice behaves differently in that region as well.
wow.
So I am a observational oceanographer. So I have a whole bunch of questions about how you measure this carbon, for instance. And so maybe that's, I have, like I say, many questions, but maybe that can be the first one is how do you measure this? Is this from water samples? Are they taken just at the seabed where your biodiversity is, or is it throughout the water column? How do you actually, you know, get these figures?
So for example, the ones I work with what's known as a multi-box cutter. That basically is it's a big device that has 9 boxes. I don't have enough space on the screen. 9 boxes that they take a chunk of the sediment, and once they are on the ship, we sieve that. And all of the animals we have there, those are the ones we use for calculating this. One way would be to you weigh them basically, and from the dry weight, you have transformation factors that you can use. That's one way for doing it. The other way is that you measure them when they're weighed, you dry them, you measure them again, and then you really burn them down until you have the ash. And then that's the ash-free dry weight. That's the technical name, let's say. That's the carbon that you have. So you can really measure them inside. So that's one way with the multi-box cutter. If you would have a net, for example, you would do the same thing. That you should troll, and whatever comes in your troll, then you do exactly the same process. And if I may already talk about the picture part, you can also do it with photographic for methods. So for example, the AVI has these OFOPs, which is the ocean floor observation and bathymetry system, which just goes along the closest seabed and takes pictures. The BAS has something which is called SACS by the acronym. It just lays on the floor, takes a picture, and goes and takes the next picture. So what they do is they measure what they get from nets. From there, they use that as transformation factors for what they find in the pictures. And from there, they measure the carbon or estimate the carbon stock.
Wow, that's a remarkable process. But does that not then also sort of limit you spatially? I mean, I've been on a ship with the OFOPs before, and you know, you go through the night with this thing. But so, I mean, how do you choose the site in which you're surveying?
So historically, and let's say until the last 10 years or so, if not a bit more, usually you try to fill the blanks, basically. Now, the idea is we already have quite a bit of station points there. Now it's to go and repeat the stations we already have. So then we can really know what happened at one transect, for example, or at one point in time. And then we just do the time series out of it.
Okay, great. Thank you very much. You explained that brilliantly. Thank you.
Yeah, I can add on to that. I have a more into the blue carbon and less the metallurgy question, since, I'm also a bit into that new field of science, but in the North Sea, which is really different from where you work. So you mainly look at the biomass, so the living animals or organisms down there on the seafloor, which is very interesting. But because you showed this graph that sequestration is for thousands of years, and I mean those animals die at some point, or the organisms. So do you think, or what's your personal opinion? Do you think you can always relate biomass directly to blue carbon in every habitat? Or is it really strictly really special to those cold South Antarctic areas? What would you say?
Well, I guess that's what we're really hoping to understand by looking at the subantarctic in particular, because you have places that are ice-free, so like the Falklands, but you also have places that are semi-ice-free, so South Georgia still has the influence of ice, for example, and then you have places like Kerguelen that are very little ice, but they occur in this location where you have the influx of polar currents, but also temperate currents, and you have animals on the seafloor that may be influenced by both. And so part of, I guess, the interesting thing is as well is that you can have similar species assemblages across all of this geographic area. So you can try and understand for particular groups and particular species as well. It's very hard to get to that point where we can easily quantify, but there's so Dave Barnes is the researcher that we keep mentioning throughout this presentation, but he's managed to look at it in bryozoans, for example, and so they are animals that you can age and that have like growth rings and through time, so they're a really good test case, but you want multiple test cases in multiple different locations to be able to answer that effectively. Yeah. But from a preliminary point of view, what we're finding in the Falkland Islands on the Burwood Bank does suggest that it's if you have a location with high biodiversity of certain groups, that you will, as a consequence, have high blue carbon storage capacity.
Interesting.
Santi, if you have anything to add to that, please do.
A bit on the Antarctic part. So there's a work that has been done by Simon Morley, if I'm getting it right, and he did in the peninsula, and they did a rather comprehensive work more with diving because it was close to the shore. And they did a bit of research in the literature and estimated that more or less of the stock that you have, roughly 10% manages to be sequestered, at least for that area. Then this is already estimation from my side. I would say that, for example, when you have a lot of sponges in a place, usually when they die, they leave all the spicules there, and all the processes in the Southern Ocean, they go really slowly because of the temperature. So I would say that a chunk of it usually gets stored, and when you have these spicule mats are called, where you have all the dead sponges, usually they already work as a trap for whatever is stored there. So you have like a safety that it could get sequestered, the chances are higher. And then on top of that, you have that where you have these mats, usually new sponges will show up and start living there. So you have like the double certainty, so to say, that the probability of sequestration will be higher.
Makes sense. Thank you.
It's possibly a massive subject that we could just keep talking about for ages. I think something that I didn't necessarily point out in the Antarctic blue carbon placemat as well is just that idea of, because blue carbon research is often focused on restoring a degraded habitat, for example. So you need to show that increase to get to that point where we want to be able to bring it into policy and carbon credits and all of the, the tangible outcomes of blue carbon research like that. And so in an Antarctic context, what we're seeing is because you've got longer lasting and increasing phytoplankton blooms, some animals on the seafloor are, reproducing in response to all that food, and so the capacity is increasing. And so to measure that increase is where Antarctic blue carbon could shift into that space, for example. Whereas if you have a high biodiversity but not the increase, then you're in a different realm of policy of trying to preserve it for blue carbon as an ecosystem service, but not within the current framework that we need to show increase at the moment, if that makes sense.
It does. sadly, that you have to show something getting better to be preserved, but that's another topic. Yeah, Rebecca, do you have another question?
Yeah, I do. I mean, I'm new to blue carbon, but I find this incredibly interesting. But I suppose one way that maybe there's a combination between our research. So we see, for instance, in the Arctic, we see changes in the temperature and the salinity of the ocean. And I wonder if there's a connection between the increase, for instance, we see in the temperature, the acidification that is pretty well known in the ocean, and if that also impacts carbon. And I suppose a second question is, how are you able to separate the physical parameters, so the changes in temperature and salinity on the biodiversity, and the carbon? Like, how does that all fit in, if that makes sense as a question?
I'll start on that one. With the acidification, it would be problematic for groups like the bryozoans, for example, because they have a carbonate skeleton. So for them, it would mean that they will lose a bit of their capacity to fix it. When we're talking about sponges, for example, you have some which calcify, but I think the bigger ones, or the most important ones, are the ones that have a silica skeleton. So they're a bit more resistant, so to say. With the temperature, that's a whole new discussion. And so far, as far as I know, at least for where I've been working, it's not a huge factor yet. It might be a bit complicated in the next years, because physiology, in the terms of physiology, they've shown that the moment you start going 0 degrees or a bit above 0 degrees, the animals already are having a huge problem to compensate for that. So if they're going to start using more resources to compensate, maybe it's quite likely that that will affect a lot their capacity for storage. And then you have the whole cascading effect of new species being introduced and everything. Then it gets a bit too complicated. And then from the temperature, at least for now, it has, at least for, again, I'm just gonna talk from what I know in the Weddell Sea, it's not extremely important yet, not directly. It's quite important how the temperatures are really affecting the sea ice dynamics, because that's what regulates then the primary production, and that's the key role there, regulating everything. They are quite, the animals in the Southern Ocean are quite food, I'll find the word eventually. They depend a lot of food. So when there's no food, they're quite inactive, but the moment that you give them just a bit of food, they react like this.
Yeah, I think that makes sense. It's maybe not a direct influence, but if it is affecting the sea ice, which we know it does, then that impacts the cover, which then in turn affects the carbon. So that makes complete sense. Thanks.
Yeah, I think it's a very big, very complicated circle, which we can, I guess, talk about for more hours than we have here. So for now, I say thank you again for you being here. And yeah, thank you for everyone on YouTube to join today. And I hope you learned a bit about blue carbon. If you have any additional questions, you can always add them to the comments, and then we will contact those two again to get the answers. So yeah, that was it for tonight. And so have a great rest of the evening. And here comes the jingle again. Bye.